Alright, so in the last unit we learned about isotopes and what they are. And again, isotopes, it's isotopes of the same atom. Basically, we're talking about the same element, but their mass will be different because the number of neutrons is different, okay? And so on your notes, it's probably important to underline, in this case, that, again, they have different numbers of neutrons inside the nucleus. And so, again, what is it that has an effect on the mass? It's going to be the presence of protons and neutrons. And so, again, they will also have an effect on the mass. If you have more neutrons, then the mass is going to be greater. If you have fewer neutrons, then the mass is going to be lower. And so all elements do have isotopes. And of course, every element in nature is a mixture of all its isotopes. And so let's look at this table here, and let's fill in the number of protons, electrons, and neutrons. And so we're looking at potassium 39, potassium 40, and 41. And so really, we don't need the periodic table of elements for this table because we're being given the actual element and the atomic mass. And so with this, again, we take that atomic mass. So for potassium 39, actually the only reason we would need the periodic table of elements is to look up the atomic number. So look up potassium on our periodic table of elements, and that's over here to the left. It has an atomic number of 19. And so again, that means that it's going to have 19 protons. And so again, because we're talking about potassium, all of them will have the same number of protons. Alright, so again, we change the number of protons and we're changing the element that we're talking about. Next is asking about the electrons. So how many electrons? Well, here we're talking about a neutral atom, and so the amount of electrons will always be equal to the number of protons because they're going to balance each other out, and the overall charge will be neutral, which means the atom itself will not have a charge, so the number of electrons will also be 19. Okay, and this is how or where isotopes are going to be different from each other. And so we have the mass. Again, we look at potassium 39 first. To determine the number of neutrons, we take that mass and we subtract the number of protons, which is right over here. So 39 minus 19, potassium 39 has 20 neutrons. And here I'm going to take 40, I'm going to subtract 19, so potassium 40 has 21 neutrons, and potassium 41 has 22 neutrons, okay? And so this area right here, this is really how these elements are different from each other. And so why all these masses listed on the periodic table of elements? Well, it would take up way too much space, and it's not really necessary. So what they do, I mean, theoretically speaking, in this case, if we did include every single isotope, our periodic table of elements would have over 300 listed on there. And again, all the elements are listed with the average atomic mass, which is what you can find down in these areas, for example. Okay, and so it is a weighted average, and so we're going to talk about what that means. Some of these isotopes are more common in nature than others, and so we call that our percent abundance. Okay, and so every single isotope has its own percent abundance. This is not something that you're going to have to calculate, but that number will always be provided for you. And so in this case, we're looking at every single oxygen atom that's present on our planet, and we're going to consider which isotope is the most common. Okay, and so let's look at our example. Nitrogen has two naturally occurring isotopes here on Earth. We have nitrogen 14 and nitrogen 15. Well, when we look at the average atomic mass, it's going to be 14 atomic mass units. So which one in this case is more abundant in nature? Well, because the average atomic mass is most similar to nitrogen 14, in this case, nitrogen 14 would be the one that's more abundant in nature. Another example that I can give you is like your grade book or our grade book. And so if I have a student and that student has, let's say, a 98, a 97, a 98, a 98, a 98, and then they have, let's say, like a 96. Okay, and so of these, here we have 1, 2, 3, 4, 5, 6. 6 different atoms, but of these 6 atoms, we have 4 of them that are 98s. We have 1 that's 96 and 1 that's 97. Well, in this case, the one that's going to be most commonly found is going to be 98 And so that means that our weighted average will be closer to this and not necessarily this or this. So how do we calculate average atomic mass? In chemistry, you want to follow steps. Okay, so make sure you have your periodic table of elements, make sure you have a calculator. And so we're going to do 3 different steps. I'm going to try to color code them for you, and that way it's easier for you to follow. All right, so here, the first example on page 29, you're being given 2 isotopes. You're being given lithium-7 and lithium-6, okay, right over here. And so we gave you the mass, and again, the number that follows your isotope, there's a mass, or we might provide you with a more detailed, more accurate mass. And so part of the information that you also need in order to figure out the average atomic mass will be the percent abundance, okay? And you can identify the percent abundance because it's always going to be listed as a percent. And that is not something that you have to figure out on your own. It'll be provided for you. All right, so the first step that you want to do is make sure that you convert, or that you change that percent abundance to a decimal. You're going to do that by moving the decimal 2 places to the left, okay? And so here, the way that you want to organize your information, I always ask my students, make sure you write your isotopes to the left, okay? Here we have the corresponding percent abundances, so from here we go here, right? We've moved the decimal places, the decimal 2 places over, so now we end up with this decimal point, okay? So now we did that for both isotopes. The second step says for you to multiply the mass of those specific isotopes. And so the mass for lithium-7 is going to be 7, so here is the mass. And the mass for lithium-6, I'm going to put that in pink, is right over here. And this is what they're multiplying by, okay? And again, they're making the connection between the corresponding percent abundances. Okay, and here we have this one over here, okay? And so we're going to add those masses together, and then that'll give us the average atomic mass. And so let's break this down. So let's look at boron, okay? And so boron, they give us 2 isotopes. They give us boron-10 and boron-11. And so again, start off by writing those isotopes. All right, so write down my isotopes. My first step, again, is is converting that percent abundance. And so here I have a percent abundance, and I'm going to put the corresponding, all right, so here's my percent abundance for boron-10, and here's my percent abundance for boron-11. All right, and my first step is changing that to a decimal point. So moving the decimal point over twice. So this first one becomes 0.198, and my second one becomes 0.802. Okay, so here is step number 1. My second step, I have to multiply the mass, and so I'm going to run out of space here, but that's okay. And so the mass that's being given to me, again, it's part of my isotope. It's right over here, or you can also find that same mass right over here. So I'm going to multiply that by 10. And for my second isotope, I'm going to multiply that by 11. Okay, and so when I do that, I'm going to make sure I use my calculator. My first isotope is going to become, it becomes 1.98, and my second isotope becomes 8.822. Okay, so that was my second step right here. Now my third step, what I'm going to do is I'm going to add these masses. So here, I'm going to add these masses. When I add them with my calculator, I'm going to end up with 10.802 atomic mass units. Okay, and again, that atomic mass unit, it's coming from right over here, so we have to make sure that we included down at my total. And that is my third step, is adding those relative masses. And then what I want to do is I want to make sure I check my work. So I'm going to look for boron on my periodic table of elements, and it's right over here. And if you look at the atomic mass, it's 10.812, and so it's very similar to what I have down here, okay? And that's one way of checking your work. All right, so let's look at the next example. Our next example is silver. So we have 2 isotopes for silver, and I'm going to go ahead and set up the work the way I set up earlier. All right, so here I listed my 2 isotopes, silver 107 and silver 108. And again, I'm going to follow my first step, right? So I have the percent abundances that were provided to me, and I'm going to write those down in red. Again, my first step is to convert those percentages to decimals. So 51.82% becomes 0.5182, and 48.18 becomes 0.4818. All right, so there's my step 1, and I'm going to go ahead and identify that as step 1. Okay. My second step, again, it's multiply their corresponding atomic mass. All right, so here are the corresponding masses, and that is my second step. Once I get those totals, I go ahead and add those. Okay, so there's my third step. Okay, so I'm going to add those. So my after I add them, I'm going to end up with 107.9636. And it's okay to go, you can round to the 100th place. And so again, my answer is 107.96. And I do need a unit, and that unit is going to be AMU. All right, let's go for one more example, and let's look at rubidium. Oh, I'm sorry, we can check our work. Okay, so I'm going to start from the far left, that way I have plenty of space. So I have rubidium 87. I'm sorry, rubidium 85 and rubidium 87. Okay, so I'm going to write that here. I'm going to write it a different way because, again, another way to write these isotopes is shorthand notation. Okay, so here's rubidium 85, and then here's rubidium 87. All right, and then I'm going to take those percent abundances that are being given to me. For 85, rubidium 85, my percent abundance, again, is 72.2%. And my percent abundance for rubidium 87 is going to be 27.8%. And again, my very first step is changing those percentages to decimals. Okay, so for rubidium 85, it becomes 0.722, and rubidium 87, it becomes 0.278. So here, again, that's my very first step. Right, my second step is multiplying their corresponding atomic masses. So for rubidium 85, they don't give me a mass to use, so I'm going to go ahead and use the masses for my specific isotope. So rubidium 85 will have a mass of 85, and rubidium 87 has a mass of 87. All right, so here's my second step. And then I'm going to get those totals. All right, so here are my totals. And of course, my final step, step 3, is going to add those relative masses. When I add those relative masses, I end up with 85.556. And again, my unit is AMUs. And here is my third step, okay, where I get to add those relative masses. All right, so I'm going to go find rubidium on my periodic table of elements. It's right over here. And the average atomic mass is 85.468, and that's pretty close, so I'm going to go ahead and stick with that. So my final answer for the average atomic mass based on those two isotopes is 85.56 AMU.